talk about vertical compressions and stretches. So in order to see how that works, let's again graph one of our parent functions, y equals the absolute value of x. We know what this looks like, but let's just quickly do a table. And we'll plot those points and continue our V-shaped graph. In part B, we have the graph 3 times the absolute value of x. So notice that we're putting a 3 outside the absolute value function. Let's again do a table of values here. All right, when x is negative 2, we take the absolute value, makes it positive, multiply by 3, and we get 6. Same idea for other values. Let's see what this looks like. So we have the point 0, 0 still. Then we have 1, 3, and negative 1, 3. And we have 2, 6, and negative 2, 6. And let's see how this looks compared to our graph in part A, the parent function. So if you see what happens, basically this got vertically stretched by 3 when compared to just the absolute value of x. So we had a vertical stretch by 3. And this is pretty straightforward because all you're doing is whatever value is outside the main part of the function, you're multiplying the y values by that, and the x values stay the same. In part C, we could again do a table if we'd like, but using the same pattern, basically whatever number you have out front is what the y values get multiplied by. So if the y values now get multiplied by a third, they're getting smaller. So we would say we have a vertical compression by a third. And a table will confirm this. So I'm choosing a few values that I know will work out a little more nicely when we multiply by a third. So if you plug in negative 3, it becomes positive, multiply by a third, you get 1. And these would be our values. If you included 6, you would get a y value of 2. Next, we're going to talk about horizontal compressions and stretches. This is what happens when you have a number that you're multiplying x by. And we're going to see what that looks like. So part A, we're asked to graph f of 3 times x, given that f of x is the square root of x. So just to make this a little easier to look at, if we're multiplying x by 3, then we're talking about the square root of 3 times x. So let's first graph our parent function, just to get an idea what this looks like. Again, we could use a table of values to help us do this. We can't take the square root of a negative, so our first number we're going to plug in is 0. I'm going to plug in some perfect squares so we get whole numbers as our outputs for y. So we have the following points here. And let's see what happens when we make a table for the square root of 3 times x. So it's a little hard to determine what are good x values to plug in. This is a little more awkward because we're taking the square root of 3 times x. So instead of thinking about the x values, let's think about the y values we want, and then we'll work our way backwards. In order to get an output of 0, we want to take the square root of 0. So let's let x be 0. If we want an output of 1, then we want to take the square root of 1, which means that 3x has to be 1, which means that x should be 1/3. If we want an output of 2, we want to take a square root of 4, which means that 3x has to be 4. So x should be 4/3. Last one, if we want an output of 3, we want to be taking the square root of 9, which means that 3x has to be equal to 9, or x has to be 3. So let's go ahead and plot these points. So some of these points are a little bit difficult to plot, but if we think about what's happening here, is our graph is actually getting horizontally compressed. It's getting smushed, so to speak. And you can see that reflected in these x values. So here we have a horizontal compression by 1/3. And the reason why is in order to get the same y values, if we're letting x be tripled, then we actually have to cut x down by 1/3 to get those same y values. We're going to see a similar idea in part B. So part B, again, we have the same parent function, the square root of x, but now we're asked to find f of 1/3 x, meaning we're taking the square root of 1/3 x. So let's again use a table of values to help us. We'll copy our previous table for the square root of x. We have the point 0, 0, 1, 1, 4, 2, 9, 3. And let's see what happens with the square root of 1/3 x. So again, it's a little awkward to think about what the x value should be. So let's fix the y values. We want outputs of 0, 1, 2, and 3. To get an output of 0, again, we want to take the square root of 0, and here x can again be 0. If we want an output of 1, that means we want to take the square root of 1, which means that 1/3 x has to be equal to 1, which means that we want to plug in 3 for x. If we want our output to be 2, that means we want to take the square root of 4, which means that 1/3 x has to be 4, which means that we want x to be 12. You can already see that we're going to get larger and larger x values, so let's just stop the table right there. So now we're going to have the points 0, 0, 3, 1, and 12, 2, which is far off our graph, but it would be somewhere around here. And that's what our graph is going to look like. So what happened here is the y values stayed the same, and our x values got much larger. They actually tripled. So here we have a horizontal stretch by 3. And y is in order to get those same y values, we had to triple our x values to balance that 1/3. So pretty much what's happening is the number that's being multiplied by x is what the x values are being divided by. Or in other words, the horizontal stretches and compressions kind of feel backwards to what you see. But as we saw mathematically, it really does make sense. But if you have 3 times x, this actually compresses it horizontally by 1/3. If you have 1/3 times x, this horizontally stretches it by 3. This is different compared to the vertical stretches and compressions we just talked about, where the number you see more logically aligns with what happens in the graph. So let's say we have a parent function f of x. And we're comparing this to a transformed function y equals a times f of bx plus c plus d. And what I'm going to do here is color code our horizontal transformations with our vertical ones. So let's start with the inside. Whatever happens directly with the x before it goes through the parent function, these all affect x, which makes sense that they're going to transform the graph horizontally. So these two are horizontal transformations. And let's now summarize what they do. So again, horizontal ones feel backwards to what you see, but mathematically it does make sense, as we saw before. B is going to be our stretch or compression factor. The number you add or subtract, that's going to be the shift. So shift left or right. Outside the function, if you have a number that you're multiplying by, or a number that you're adding or subtracting at the end, these are going to affect the graph vertically. So A and D are both vertical, and they seem more straightforward. And to recap what happens, the number out front is again our vertical stretch or compression factor. The number we add or subtract is our vertical shift, which is going to go up or down. So the pattern that you're probably going to recognize is when we add or subtract, this translates into a shift. When you multiply or divide, this translates into a stretch or compression. And if you have multiplication by a negative, that's going to be a reflection. If you'd like to summarize the reflection further, when you have the negative with the x, you're changing the x values, which means you're going to flip over the y-axis. When the negative is out front, or with the y, that's affecting the y values, which means that the y values change and the graph is reflected over the x-axis.